Welcome all learning enthusiasts. In my earlier video, we learned about the rockets. In today's video, we will dive further into the rocket engine. Let's start with types of rocket engines. The most common classification is based on the type of propellant used and the engine cycle. A. Solid rocket engines. B. Liquid rocket engines. C. Hybrid rocket engines. Already discussed in my earlier video. Link shared in the description box. We start with D. Cryogenic rocket engines. 1. Cryogenic engines use extremely cold propellants. Typical combination. A. Liquid hydrogen, minus 253 degrees Celsius. B. Liquid oxygen, minus 183 degrees Celsius. 2. These engines produce the highest specific impulse among chemical rockets because hydrogen has a very high exhaust velocity. 3. Challenges include A. Complex insulation. B. Difficult storage. C. Turbopumps operating at extremely low temperatures. For example, India's CE-20 is a cryogenic engine that powers the upper stage of LVM-3. It uses a gas generator cycle and is continuously being upgraded for future missions, including Gaganyaan and heavier launch vehicles. E. Semi-cryogenic rocket engines. It uses 1. Liquid oxygen LOX. 2. Refined kerosene RP1 or kerosene. Compared with hydrogen engines, they 1. Produce much higher thrust. 2. Are easier to handle. 3. Reduce launch costs. 4. Improve payload capacity. Next, SE-2000 engine. 1. India's SE-2000 engine represents a major technological leap. 2. It employs an oxidizer-rich stage combustion cycle. 3. It produces about 2,000 knots of thrust. 4. It is intended for future LVM-3 upgrades, reusable launch vehicles, and the next-generation launch vehicle (gslv). F. Hypergolic engines. 1. Hypergolic propellants ignite automatically when fuel and oxidizer meet. 2. Advantages. Extremely reliable ignition. Multiple restarts. Excellent for spacecraft maneuvers. 3. Disadvantages. Highly toxic. Expensive handling procedures. 4. These engines are widely used for orbital corrections and satellite propulsion. G. Green propellant engines. 1. Researchers are replacing toxic hydrazine with environmentally friendly propellants. 2. Benefits include reduced toxicity, lower handling costs, safer launch operations, better environmental performance. 3. Green propulsion is expected to become increasingly important for future satellites. I would like to request the viewers, once again, to pause the video and read the infographics for detailed understanding of the concept. Next, we learn about rocket engines by working cycle. The engine cycle determines how propellants reach the combustion chamber. 1. Pressure-fed cycle. Compressed gas pushes propellants into the chamber. Simple, but suitable only for smaller engines. 2. Gas generator cycle. A small portion of propellant powers a turbine, after which exhaust gases are discarded. B. Examples Merlin CE-20. C. Advantages. Simplicity. Reliability. D. Disadvantage. Slight efficiency loss. 3. Staged combustion cycle. A. Instead of discarding turbine gases, they enter the main combustion chamber. B. Advantages. Higher efficiency. Higher chamber pressure. Better performance. C. Disadvantages. Complex engineering. Higher development cost. 4. Full flow stage combustion. A. Advantages. Highest efficiency. Longer engine life. Better reusability. B. Example. SpaceX Raptor. 5. Expander cycle. A. Liquid hydrogen first cools the combustion chamber. B. The heat vaporizes the hydrogen, which then powers the turbine before entering combustion. C. Advantages. Excellent efficiency. Fewer moving parts. D. Disadvantage. Limited maximum thrust. 5. Electric pump-fed cycle. A. Instead of turbines, electric motors drive the pumps. B. Advantages. Simpler plumbing. Lower development cost. C. Suitable for small launch vehicles. Startup companies. D. Example. Rocket Lab Rutherford. Next important aspect. Rocket engine cooling systems. A. Regenerative cooling. This is the most widely used method. Before entering the combustion chamber, cryogenic fuel flows through channels around the chamber and nozzle. This process absorbs heat, prevents melting, preheats the propellant, improves efficiency, supports engine reuse. It is used in engines such as Merlin, RS-25, Raptor, and India's CE-20. B. Ablative cooling. A special protective lining gradually burns away, carrying heat with it. Viewers can pause the video and read the infographic content. C. Film cooling. A thin layer of cooler propellant forms a protective film along the combustion chamber wall. D. Radiative cooling. Heat naturally radiates into space. Viewers can pause the video and read the infographic content. E. Dump cooling. Some propellant is deliberately released along the nozzle wall for cooling rather than combustion. F. Transpiration cooling. This futuristic method allows coolant to seep through microscopic pores in the chamber wall. Viewers can pause the video and read the infographic content. Next, rocket testing includes 1. Component testing. Each component is tested individually. Viewers can pause the video and read the infographic content. 2. Hot fire testing. The complete engine is fired while securely mounted on a test stand. 3. Qualification testing. The engine operates beyond normal mission limits to verify safety margins. Viewers can pause the video and read the infographic content. 4. Static fire test. Even after integration with the rocket, the engines are often ignited briefly while the vehicle remains securely held on the launch pad. Next, artificial intelligence in rocket engines. AI in engine design. Today, AI algorithms rapidly optimize injector geometry, cooling channels, combustion chamber shapes, nozzle contours, material selection. This significantly shortens development time. B. AI in manufacturing. Modern rocket engines increasingly use additive manufacturing or 3D printing. AI monitors print quality, internal defects, dimensional accuracy, material stress. This reduces waste and improves reliability. C. Digital twins. A digital twin is a virtual replica of a rocket engine. It continuously receives sensor data from the real engine and predicts wear, fatigue, remaining service life, potential failures. Engineers can identify problems before they occur. D. Predictive maintenance. Benefits: lower maintenance costs, faster turnaround, higher launch frequency. E. Combustion instability detection. 1. AI detects abnormal sensor patterns and can recommend corrective actions before catastrophic failure. F. Autonomous flight. During ascent, AI can monitor engine health, detect anomalies, optimize trajectory, improve fuel efficiency, support autonomous mission decisions. Finally, several revolutionary concepts are under active development. 1. Nuclear thermal propulsion. Advantages: nearly double the specific impulse of chemical rockets. Faster missions to Mars. Reduced propellant requirements. 2. Nuclear electric propulsion. Such engines offer extremely high efficiency, long-duration deep space missions. Although thrust is low, they're ideal for cargo transport across the solar system. 3. Aerospike engines. Such engines automatically adapt to changing atmospheric pressure. Potential benefits: higher efficiency, better performance from sea level to vacuum. 4. Rotating detonation engines. These engines use continuously rotating detonation waves instead of conventional combustion. Potential advantages include greater efficiency, reduced fuel consumption, simpler design. They remain an active area of experimental research. Thanks for watching. I hope viewers enjoyed this in-depth analysis.